So we're here on review problem 579. 579 says choose reactants that would yield the following net ionic equations and then write the molecular equations for each. So we have some net ionic equation given to us, HCO3 minus plus H plus yielding H2O and carbon dioxide. H2O and carbon dioxide. All right? So the molecular equation, this HCO3 minus would need something like maybe potassium, K plus. In the ionic equation, this compound here would need something that wouldn't interact with potassium and form any other compound like Cl. So we have Cl minus. So we have potassium plus HCO3 plus Cl plus H plus, Cl minus. So then the molecular equation was HCl plus potassium bicarbonate, CO3. And the products are going to be potassium chloride and water and carbon dioxide. Or this water and carbon dioxide could be in the form of potassium or bicarbonate or carbonic acid, H2CO3. All right, so that's A. Iron and hydroxide coming to form iron hydroxide. Iron, Fe forming an hydroxide ion, OH minus coming together to form FeOH. Is it iron 2? Iron 2, yes. All right, so what did the iron come with? Maybe chloride? Maybe, let's see if we can get a better pen here for us. FeCl3 or 2, FeCl2. So we have iron chloride plus sodium hydroxide maybe, right? Because sodium and chloride are not going to form any insoluble compound over here. So the result would be iron hydroxide and sodium chloride, right? That's okay, that works fine. So that's a molecular equation that would give the net ionic equation of that one. Okay. The next one, barium sulfate. So we have the barium ion and the sulfate ion coming together to form barium sulfate. Okay. So we want whatever the counter ion that came with barium and the counter ion that came with sulfate. We don't want them to interact with each other. So barium could have come with chloride, right? Whoops. Barium chloride, and if we have barium chloride, oh, you know what? I don't know if I was balancing those previous equations. I'll have to make sure I balance this one, but go back to those previous two there and make sure that I didn't remember that you have to balance them, right? Barium chloride plus, we could just do sodium sulfate, SO4, and then the products would be barium sulfate, and that's our solid, right? And then the other product would be sodium chloride, NaCl, and that would be aqueous. Okay, now let's see if we balance this equation here, we see that we're going to need 2 sodium chlorides, right? Okay. So the next one, silver and sulfate, or sulfide, silver and sulfide. We have Ag plus, 2 of them coming together to form with S2 minus to form Ag2S, silver sulfide. This is the solid, right? Well, silver has to come with something that it's not insoluble with. It can't be with chloride or iodide or halogen. Halogens are easy to choose. It can't be an oxide. Silver oxide is a solid. It can't be sulfide, right? So silver usually comes with, if you want to get the ion, you have to use the nitrate form. Nitrates are not soluble, are soluble. Nitrates are soluble, so silver nitrate. Sulfide are generally insoluble as well, so what's going to come with the sulfide? We can always use sodium, Na2S, sodium sulfide will be soluble. All right, so then that will give us sodium nitrate, NO3, and we're going to need 2 of those sodium nitrates to balance this one, and the other product is going to be the Ag2S, 2 of these here, All right, so there it is. Okay, good. All right, zinc oxide and acid. So we have zinc oxide, solid, with H+, which is acid, right? And the products are going to be zinc ion and water. That is the net ionic equation. So what could have come with the H+? Well, could it be HCl, right? HCl will deionize or dissociate and ionize to give the H+. The zinc oxide started off as that, right? So the products here are going to be, again, your zinc ion and your water. So that's all you have to do for that one. Let's see, is it balanced? We're going to need 2 here. Oh, we also need to have the Cl- ion there as well. Oh, wait. This is the molecular equation. So in the molecular equation, it's going to be zinc chloride like that. Take this. Right? Very good. 2 protons, 1 oxygen, 1 oxygen. 2 chlorides, 1 zinc, 1 zinc. All right. All right, that's 579. 581. Calculate the molarity of a solution prepared by dissolving 4 grams of sodium hydroxide in a total volume of 100 milliliters. We're looking for molarity, which is the same as moles per liter, right? So we want to know the molarity of 4 grams of sodium hydroxide. 4 grams of sodium hydroxide, NaOH, in how many milliliters? 100 milliliters, which is 0.1 liters. All right? Liters on the bottom, liters on the bottom. We need moles on top now. So we just need to know how many grams of sodium hydroxide are in 1 mole. Oh, no. Yeah, 1 mole of sodium hydroxide. So then we'll be in moles of sodium hydroxide per liter of solution. All right? So sodium hydroxide, sodium is 23. Oxygen is 16. Hydrogen is 1. So 6, 7, 8, 9, 10, 2, 3, 4. So that's 40 grams for every mole. So we have 4 divided by 0.1 divided by 40, right? So is that just 1 gram? Gram. Oh, no, sorry, 1 molar. 1 molar. So the answer is 1 molar for that one. Now, as B, 16 grams of calcium chloride in a total volume of 250 milliliters. Okay, so this is just another problem. 16 grams of calcium chloride in a total volume of 250 milliliters, or 0.250 liters. All right, what's the molarity, or moles per liter? Well, calcium chloride, calcium is 40, chloride is 23, no, 35, 35.4. Times 2 plus 40, 110.8 grams for every 1 mole. We have, all right, so we're going to finish up this problem here. 16 grams. 16 divided by 0.25 liters divided by 110.8. So that's 0.578 molar. All right, 0.578 molar. Let's double check on those ones. 581. Yes. Okay, good. What's next? 583. How many milliliters of 0.265 molar sodium acetate are needed to supply 14.3 grams of sodium acetate? So, question is, milliliters of solution. And we want 14.3 grams. 14.3 grams of NaC2H3O2. That's how many grams of that stuff we want. We can convert that to moles to know how many moles of that stuff we want. So we have to determine the the molar mass of sodium acetate. So it says here that molar mass of sodium acetate is 82.3. 82.03. 82.03 grams for every 1 mole of sodium acetate. NaC2H3O2. So now we're in moles of sodium acetate. And how many moles of sodium acetate do we have for every liter? Because we need to get into liters. Okay, so molarity is moles per liter. So if we take 0.265, there's 0.265 moles for every 1 liter. So 14.3 divided by 82.03 divided by 0.265, and that should be how many liters? 0.6578, or how many milliliters? 657. So the question was, how many milliliters of that stuff are needed to supply that many grams? 583, 657.8, 658 milliliters. All right, great. All right, 585. Calculate the number of grams of each solute that has to be taken to make each of the following solutions. All right, 585 now. How many grams of sodium chloride do we need to make 125 milliliters of 0.2 molar? 0.125 liters, 0.2 moles per liter. Sodium hydroxide, is that what this is? Sodium chloride, 58 grams for every 1 mole. All right? So you see the liters cancel out, moles cancel out, and we're in grams of material. So you always take the amount of liters you want, the molarity you want, and the molar mass that you have. Okay? And that'll always tell you your answer. So that is 0.125 times 0.2 times 58. 1.45 grams. Okay? The next one, 250, 0.250 liters. The molarity is 585B, 0.360 moles per liter. And this is 180 grams per mole. That's what sucrose, or glucose is. I know that, I just happen to know that one because I'm always working with it. 180 grams per mole. So 0.25 times 0.36 times 180. 16.2. All right, and we can double check here for the molar mass of glucose. Molar mass of glucose. Okay, let's see, 180.16. All right, C, 250 milliliters of 0.25 molar sulfuric acid. 250 milliliters, or 0.250 liters. .250 moles per liter, and this many grams, so we need to know the molar mass of sulfuric acid. Molar mass of sulfuric acid. Okay, so there, for every 1 mole of H2SO4, it's 98.1 grams of H2SO4. So this will tell us how many grams of H2SO4 we need to weigh out. Okay, so 0.25 times 0.25 times 98.1. All right, so for those ones we got 1.45, that was 585. Let's double check on those ones. 1.45, 16.2, and 6.13. Good. All right, 587. If 25 milliliters of 0.56 molar sulfuric acid is diluted to a volume of 125 milliliters, what's the molarity of the resulting solution? Well, for this one we use what's called the dilution equation. The dilution equation is the initial concentration, C1, initial volume, and the relationship between those two is equal in a dilution problem to the final concentration and the final volume, right? And you can either memorize that or you can rederive it every time you need to remember it based on a simple story that I'll tell you in class about baskets and apples, how many apples there are per basket. Or you can just take some knowns and try to fit them in and rederive the equation as well. But we're looking for 25 milliliters of 0.565. So we have initial 25, initial volume is 25, initial concentration is 0.565. This is molarity, this is milliliters. So these need to be molarity in milliliters over here. What is the final molarity? It's a diluted to a volume of 125. So what's the final concentration of molarity? All right, so we have 0.565 times 25 divided by 125. And that's x equals 0.113. And again, my units were molar. So that's the final molarity. All right? So that's basically 565 divided by 5, right? Yeah. All right. 589. To what volume must 25 milliliters of 18 molar sulfuric acid be diluted to give me 1.5 molar? Okay, so that's 589. 587. So now we're at 589. What volume is 25 milliliters of 18 molar? Concentration, 18 molar. Volume, 25 milliliters. What volume, if we want the final concentration to be 1.5? Final concentration is 1.5, then what does the resulting volume need to be? Well, 18 times 25 divided by 1.5. And the answer here is x needs to be 300. X equals 300, so the final volume needs to be 300. Okay? Final volume is 300. All right. What volume? Yeah. So you always have to double check. You have to double check that they're not asking for how much water needs to be added. Because if they were to ask how much water needs to be added, you'd have to go from 25 to 300. That's 275 milliliters of water extra. But they're asking for what the final volume actually will be. Okay? So 589, 591. How many milliliters of water must be added to 150 milliliters of 2.5 molar to give 1 molar? 2.5 molar, whoops, concentration 1, volume 1, concentration 2, volume 2, final. Okay, so 2.5 is the initial concentration, is that right? 591. 150 milliliters, concentration 1, 2.5 molar, volume 1, 150 molar, and the final concentration we want to be 1 molar. So what's the final volume going to be? Now, this is one of those problems. They don't ask us what the, so this is 2.5 times 150. 375 divided by 1, so 375, that's what X is, and that's the final volume that you need to have. But that's not what the question is. We take 375 minus how much we initially started with to find out how much water we need to add. So 225 milliliters of water needs to be added. So how many milliliters of water must be added? 225 milliliters. Okay? So again, 375 is the final volume, but they asked how many milliliters of water you need to add. Well, you started with 150, so you had 225 to get to that final volume. 593. Calculate the number of moles of each of the ions in the following solutions. All right? We're done with that dilution equation. 32 milliliters, 0.45 molar calcium chloride. 32.3 milliliters. So there's 0.455 molar, that means moles per liter, of calcium chloride. And we have 32.3 milliliters, or 0.0323 liters, right? So this will tell us how many moles of calcium chloride we have. And we'll just find that answer really quickly. 0.455 times 0.0323. So that's 0.01469. And that's how many moles of calcium chloride there is. Now, we could have included another step here. If we wanted moles of just calcium, we could have said for every 1 mole of calcium chloride, there's 1 mole of calcium, and then the answer would be the same, but it would be just how many calciums there are, right? But instead of doing that, we can just go to moles of calcium chloride and know that for every mole of this, we have 1 mole of calcium. So that's how many moles of calcium we're going to have. For every mole of this, we're going to have twice as many calcium. So whatever that number is times 2 is how many moles of calcium we're going to have. Okay? 593, let's make sure we're doing this right. 593A. Didn't miss anything? Yeah. Okay? So 593B, 50 milliliters, 0.408 molar aluminum chloride. 0.408 molar aluminum chloride, AlCl3. And the liters of that stuff, 50 milliliters, right? And this is how many moles of aluminum chloride now, AlCl3, right? So 0.408 times 0.05, that's 0.204. And that's how many moles of aluminum we're going to have. It's how many moles of aluminum chloride, but it's also how many moles of aluminum. For every 1 mole of aluminum chloride, we have 1 mole of aluminum. And we just multiply that by 3 to find out how many moles of chloride, which is 0.0612 moles of the chloride ion. All right, so this is how many moles of the aluminum ion. That's how many moles of the chloride ion. All right? That's what they asked us to do, the number of moles. Calculate the concentration of each of the ions now. Okay? So 595. Calculate the concentration of each of the ions. 595. Well, if we have 0.25 molar chromium nitrate, 0.25 moles for every 1 liter chromium nitrate, NO33. Chromium 2 nitrate. All right. So if that's how many moles I have per liter, then how many moles of chromium am I going to have? Well, for every 1 mole of chromium nitrate, NO32, I'm going to have 1 mole of chromium. All right. So it's going to be 0.25 molar in chromium. And this answer here will be molarity of chromium, right? Because it would be moles of chromium per liter of solution. Moles of chromium nitrate crossed out, and we're in moles of chromium per liter of solution. And that's what we wanted to know, moles of chromium ion per liter of solution. And I could, if I want to know how many nitrate ions there are, well, for every 1 mole of chromium nitrate, it looks like there's 2 moles of nitrate. And then this would tell me how many moles of chromium nitrate. So the 0.25 times 2, and that would give us 0.5 molar. All right, so that's pretty straightforward. So if we see 0.1 molar copper sulfate, we know we have 0.1 molar copper and 0.1 molar sulfate. So that's B. All right? Same idea here. Whatever the molarity of your salt is here, whatever the molarity of the salt is here, and then how many moles of the specific, this is the moles of the salt, and this is the moles of the specific ion. And because there's 1-to-1 ratio for, in the case of copper sulfate, 1 copper for every copper sulfate, 1 sulfate for every copper sulfate, it's just going to be 0.1 molar copper and 0.1 molar sulfate ion. C. 0.16 molar sodium phosphate. Well, 0.16 times 3, right, because there's 3 moles of sodium for every mole of sodium phosphate. So it's 0.48 molar sodium and then 0.16 molar phosphate. D, aluminum sulfate, 0.075. 0.075 times 2 is 0.15, and that's the molarity of aluminum. 0.075 times 3 is 0.225, and that's the molarity of the sulfate. Okay? 597. In a solution of aluminum sulfate, the aluminum plus 3 concentration is 0.125 molar. How many grams of aluminum sulfate are in 50 milliliter of this solution? All right, in a solution of aluminum sulfate, the aluminum concentration is 0.125 molar. So there's 0.125 moles per liter of aluminum. So aluminum sulfate, write this one down, 0.125 moles of Al plus 3 for every 1 liter of solution, right? And we want to know how many grams of aluminum sulfate that is. Well, if you had 0.125 moles of aluminum, for every amount of that, there must be 0.125 times 2, or 0.25 moles of Al2SO4, 3, right? There must have been 0.25 moles of aluminum sulfate. And for every 1 mole of aluminum sulfate, Al2SO4, 3. So here we need to identify the molar mass of aluminum sulfate. So this is going to be how many grams of aluminum sulfate. And then that's all we need to know, right? 342.15. That's how many grams there are in every 1 mole of aluminum sulfate. Oh no, we also need to know that we're trying to get grams of aluminum Al2SO4, 3, aluminum sulfate. So we need to go to, right now we're in grams of aluminum sulfate per liter, right? So we have to get rid of liters. And we know we had 0.05 liters. That's our 50 milliliters. Okay? So we take our 0.125, yeah, for every 0.125, 0.25. This could have been a 1 to 2 instead, but it's the same thing. So 0.125 divided by 0.125 times 0.25, or, yeah. Times 342.15 divided by 1 times 0.05. So I'm looking at 4.28 grams of aluminum sulfate. That's right. All right, so that's 597. We missed it. What did we miss? Let's try that again. Make sure I had the right molar mass, did I? Aluminum sulfate, 342.15 grams per mole. So what was the question again? In the solution of aluminum sulfate, the aluminum concentration is 0.125 molar. Well, if there's 0.125 moles of aluminum per liter, then that should be twice as many moles of aluminum sulfate. Oh, no. Let's see. For every 1 mole of aluminum, there's a half. So you get 2 moles of aluminum for every 1 mole of aluminum sulfate. So that was the problem there. For every 1 mole of aluminum sulfate, there's 2 moles of aluminum. All right? So let's see if that fixes things. 0.125 divided by 2 times 0.05 times 342.15. All right, so that gave me 1.06. 1.07. Yeah. Okay. So that was my mistake. We have to pay attention to that too. For every mole of aluminum sulfate, you have 2 moles of aluminum there. All right. Good. 599. How many milliliters of 0.258 molar nickel chloride solution are needed to react completely with 20 milliliters of 0.153 molar sodium carbonate? All right. So we have 20 milliliters, 0.153 molar sodium carbonate. So we have 0.153 moles of sodium carbonate for every 1 liter. And we have 20 milliliters of that, or 0.02 liters of that stuff, of the Na2CO3 solution. So this tells us how many moles. If we multiply the molarity times the liters, it tells us how many moles of sodium carbonate we had in that solution. And we want to know how many moles of, or how many milliliters of a 0.258 molar nickel chloride. So we have to identify our equation, right? Nickel chloride 2, 3. Nickel chloride plus sodium carbonate. Products here are going to be sodium chloride and nickel carbonate. Okay? All right, gotta go. Myself doing some problems. Okay, so we're on number 599. How many milliliters of 0.258 molar? 0.258 moles of, what is it? Nickel chloride, NiCl2, for every 1 liter of solution. Right, that's what molarity means. Are needed to completely react with 20 milliliters of 0.153 molar sodium carbonate. I guess that's what we want to start with, 0.153 molar of sodium carbonate. 0.153 molar of sodium carbonate. All right, and that's how many moles there are for every 1 liter. So this is moles now. 0.153 moles for every liter of sodium carbonate, and we have 20 milliliters of that stuff, or 0.02 liters of Na2CO3 solution. Okay, so this will tell us how many moles of sodium carbonate. And now we need the molar ratio, the stoichiometry between sodium carbonate and nickel chloride to form nickel carbonate. All right, so we have sodium carbonate, Na2CO3, plus nickel chloride, NiCl3, correct? 2, sorry, this is 2 chloride. All right, and the products here are going to be NaCl and NiCO3. All right, and yes, that's right. Nickel carbonate is a solid here. Okay, these are all liquids. So we have to balance this equation. So we need 2 sodium chlorides. We have 1 carbonate and 1 nickel, so that's it. So for every sodium carbonate, we're going to get 1 nickel carbonate. All right, so we have this many moles per liter of sodium carbonate. And this is how many milliliters of sodium carbonate we have, right? And we see that for every mole of sodium carbonate, there's 1 mole of nickel chloride. So for every, we're in moles of sodium carbonate, so for every 1 mole of Na2CO3, it's 1 mole of nickel chloride, right? So, and we want to go to, or we want to answer the question about 599, the question is how many grams of nickel carbonate will be formed? All right, so there's 1 mole of, so let's see, what do we say here? How many milliliters of that many nickel chloride solution are needed? Oh, so that's the first question. How many milliliters of this solution are needed? Well, now we're in moles of nickel chloride, and we have 0.258 moles of nickel chloride for every 1 liter. So this will tell us how many milliliters, or how many liters right now, of the nickel chloride solution we need. Okay? So we have then 0.153 times 0.02 divided by 0.258. And that looks like 0.0118 liters, or 11.8 milliliters. Okay? So 599, the first part is 11.8 milliliters. So that always rounds up to 11.9. And then the question is how many grams of nickel carbonate will be formed from the reaction. Oh, look, it already gave us the reaction. I didn't have to come up with the reaction. So how many grams of nickel carbonate will be formed? Well, if this is how many moles, let's see, this is how many, let's see, for that one we're looking for how many grams of nickel carbonate. So how many grams of nickel carbonate? And if we had 0.153 moles of sodium carbonate, and for every mole of sodium carbonate, we're going to get 1 mole of nickel carbonate. All right, that's how many moles we have per liter, 0.02 liters. Does it say how many milliliters? All right, yeah, so we can just tell from here, this is how many moles of, that's how many liters of sodium carbonate there. This is how many moles of sodium carbonate per liter. This is how many liters of sodium carbonate. So we'll be in, if we multiply this molarity by liters, we'll be in moles of sodium carbonate. And for every 1 mole of sodium carbonate, we get 1 mole of nickel carbonate. All right, and then we just have to identify the molar mass of nickel carbonate. Molar mass of nickel carbonate. 118.702. Grams of nickel carbonate for every 1 mole of nickel carbonate. All right, so then we have 0.153 times 0.02 times times 118.702. And that's 0.363 grams of nickel carbonate. 599, yeah. Okay, I got it. Okay, so that's 599, 5101. What is the molarity of an aqueous solution of potassium hydroxide if 21.34 milliliters is exactly neutralized by 20.87 milliliters of 0.116 molar HCl? That's the molarity of HCl. 21.34 milliliters, or 20.78 milliliters of this stuff. which is 0.0278 liters. So this is how many moles of HCl there are for every 1 liter. This is how many liters of the HCl solution we had. So this, multiplying those two together, will tell us how many moles of the HCl there were. What is the molarity of an aqueous solution of potassium hydroxide? What is the molarity of an aqueous solution of potassium hydroxide? 21.34 mole. Okay, so for every, now we're in moles of HCl, and for every 1 mole of HCl, we're going to consume 1 mole of potassium hydroxide. And now we're in moles of KOH. We just have to divide by liters of KOH, which is 21 or 0.02134 liters of KOH. All right? And this then tells us the molarity of KOH. Now that was using a 1-to-1 ratio, 1 mole of HCl for 1 mole of KOH. Now I know that's going to happen because I can visualize this reaction in my head, right? The reaction of HCl with KOH. But you need to know this reaction before you can actually say that it's a 1-to-1 ratio, right? But this is going to be potassium chloride and water, right? And I can see that that's balanced just like it is because it's a 1-to-1 ratio. Therefore, I knew that that was going to be the answer there. Or but we have to write this anyways because it told us to. So 0.116 times 0.02078 divided by 0.02134, and it looks like the molarity of the KOH solution was 0.113 molar. All right, and that's what the question is. What's the molarity of the potassium hydroxide solution? All right, good. So that's 5101. 5103. Aluminum sulfate is used in water treatment to remove fine particles suspended in water. When made basic, a gel-like precipitate forms that removes the fine particles as it settles. In an experiment, a student planned to react aluminum sulfate with barium hydroxide. How many grams of aluminum sulfate are needed to react with 85 milliliters of 0.5 molar barium hydroxide? So we have, or 0.05 moles for every 1 liter of barium hydroxide. No, barium hydroxide. So 0.05 moles per liter of barium hydroxide. And they told us how many milliliters of that stuff, or how many liters of that stuff, right? So this is the liters of barium hydroxide. This is the liters of barium hydroxide too, also, right? All right, so molarity times liters leaves you with moles of barium hydroxide. And we need to know the ratio, right? A student planned to react that with that. How many grams of aluminum sulfate are needed? Well, we need to know the ratio now. So we'll do our aluminum sulfate, AlSO4, Al2SO4 3, right? Plus barium hydroxide. Product is barium sulfate and aluminum hydroxide, AlOH3, right? All right, so we are going to get 2 of these aluminums because we started with 2 here. 3 sulfates, so we needed 3 there, and we needed 3 here. And that gives us our 6 hydroxide ions. Okay, so it's for every 3 moles of barium hydroxide, we consume 1 mole of aluminum sulfate. So there's 3 barium hydroxides for every 2 aluminum, no, 1, for every 1 aluminum sulfate. All right, so now we're in moles of aluminum sulfate, and the question is how many grams. So we have to identify the molar mass. We have to identify the molar mass of aluminum sulfate, because for every 1 mole of Al2SO4 how many grams is that? 342.15 grams of Al2SO3. Al2SO4, sorry. And then that'll give us grams of aluminum sulfate that we need. Okay? So we have 0.05 times 0.085 times 1 divided by 3 times 342.15. So that's 0.484, 0.485 grams of aluminum sulfate for number 103. Okay, 105. How many milliliters of 0.105? Let me erase this one. Number 5. 105. How many milliliters of 0.15 molar iron chloride solution are needed to react completely with 20 milliliters of 0.045 molar silver nitrate? 0.045 moles of AgNO3 for every 1 liter. That's molar, right? That's the concentration, 0.045 molar silver nitrate solution. And we have 20 milliliters of that, or 0.020 liters of the AgNO3 solution, right? So now we're in moles of silver nitrate, and we need to go to moles of iron chloride. So silver nitrate and iron chloride, AgNO3 plus FeCl3, iron 3 chloride. Silver nitrate plus iron chloride, iron 3 chloride is silver chloride plus iron nitrate. Okay, 3 nitrates because this is iron 3 chloride here. Okay? So, we have to balance this. We have 3 nitrates, so 3 here, and we're going to get 3 of those. Okay, so we have 3 silvers, 3 nitrates, 3 nitrates. 1 iron, 3 chloride, 3 chlorides. All right, so for every, we're in moles of AgNO3 right now, and for every 3 moles of AgNO3, right, then how many moles of FeCl3 are we going to need? We're going to need just 1 mole of FeCl3, all right? And then we identify the molar mass of iron chloride, how many grams of silver chloride are formed. Oh, sorry, I was going after the iron chloride, but we want to know how many moles of silver chloride. Well, it's a 1-to-1 ratio, then, or 3-to-3. So we need to find the molar mass of silver chloride. Molar mass of silver chloride. Oh, there it is, 143.32. So 1 mole of our AgCl is 143.32 grams of AgCl. All right, and so this will tell us how many grams, how many milliliters. What am I after? How many milliliters? Oh, nuts. So the second part of the question is this. The first part of the question was milliliter, or how many milliliters of 1.15 molar FeCl. So the second part of the question is this. So while we're here, let's get this. 0.045 times 0.02 times 3 divided by 3 times 143.32. So this is 0.129 grams of AgCl. So that's how many grams of silver chloride we'll expect to get. 105, part B, is 0.129 grams of silver chloride. And now the first part, we have to go back here and go, this is going to be the iron chloride, right? So there's 1 FeCl3. And then this is moles of iron chloride for every mole of silver nitrate, right? So 1 mole of silver iron chloride, and we know that our solution is 0.15 molars. So 0.15 mole of FeCl3 for every 1 liter of solution, right? That's what it is. It's 0.15 molar. So that's how many. This will tell us right here how many liters. And we can take that liters to 1 liter is 1,000 milliliters of that iron chloride solution. So we were in moles of silver nitrate, or molar silver nitrate, multiplied by liter, went moles of silver nitrate. Divided by moles of silver nitrate, we got to moles of iron chloride. divide by moles of iron chloride, or molar, multiplied by molar, or divide by molar. So, all right, so we are in moles of iron chloride. We multiplied or divided by the molarity here. Divided by the molarity, how many moles per liter? And then converted liters to milliliters. All right, so we have 0.045 times 0.02 divided by 3 divided by 0.15 times 1,000. And it looks like 2 is our answer, 2 milliliters. So let's double check that. 5105, 2 milliliters. All right, got it. 5107.